Cool. So this will be the second lecture in this series on scaling algorithms. And today we're going to cover how to study scaling algorithms and analyze them using the framework of convex optimization. So first, what we'll do is we'll discuss the matrix scaling problem in full details with like formal definitions. And we'll introduce the Sinkhorn scaling algorithm for it, which is a really, really old algorithm for matrix scaling, which has been used in a variety of different communities. From then, we'll discuss the plan, which is to analyze the Sinkhorn algorithm using convex optimization. So before we do the analysis, we'll just give a few background definitions on what is convex optimization and how like certain properties of convex functions. After that, we'll do the convex optimization analysis for standard matrix scaling. This was actually done in an old work by Lineal, Sarandisky, and Woodgerson to study approximations to the permanent. And finally, we will give a much improved analysis for the strongly convex setting. I'll define what strongly convex is, but we'll give a much improved analysis for special kinds of inputs for matrix scaling. And this is actually what we will generalize to give our main application to statistics in the last lecture. So first we'll do regular convex optimization, and then we'll see how to improve all the results for the strongly convex setting. Okay, so first, what is matrix scaling and what is the Sinkhorn scaling algorithm? Right. So matrix scaling is you're given an n by n matrix and you scale it by left-right action. So you scale the rows by some numbers and you scale the column by some numbers. And going back to the orbit perspective from last lecture, the null cone that we're trying to distinguish between is if you consider the matrix as the weight of a bipartite graph, then those graphs with no bipartite matchings will be in the null cone. So those graphs that can be scaled to 0 will be those without bipartite matchings. Cool. And like, what is exactly matrix scaling? What do we want to do for matrix scaling is you want to make all the row and column sums to be the same or equal to 1 or equal to 1 over n, depending on the normalization. And the row sums are equal to the sum of the squared entries of the ith row, and the column sums are equal to the sum of the squared entries of the jth column. This is just a particular variant we choose, so it generalizes better. I think the original one, they took inputs as non-negative matrices, and then they actually consider the row and column sums. But it's all equivalent up to this transformation. Cool. And what do we want to do is we want to scale the matrix to be doubly balanced, where doubly balanced is measured, the error to doubly balanced is measured in this way. It's not super important what the formula is, just know that it's the difference from the row sums to the uniform vector, right? So it's the L2 norm squared of how far your row sums are from being the same and column sums are from being the same. All the normalizations make the formula a little bit more confusing, but yeah, that's the main idea. Cool. So the matrix scaling problem is you're given an arbitrary matrix A and you're given a precision delta, and you're asked, can you scale A by left-right scalings to some matrix with distance to doubly balanced at most delta? And so if yes, you want to find the scalings. And if no, then you want to return fail, right? And a very old algorithm that is actually pretty natural, like as a first step for what you do, is you have these two conditions that you want to satisfy. You want the rows to be the same and the columns to be the same. Each of those is very, very simple to solve on its own, right? So to scale the rows, you can just normalize each of the rows, and similar for the columns. So the Sinkhorn scaling algorithm is just to do these repeatedly, right? So if A is not row normalized, then you normalize the rows. And if A is not column normalized, you normalize the columns. But as you normalize the columns, you will mess up the rows and vice versa. So you hope that this thing converges at some point. And so you just output, if it does converge at some point before t iterations, you output it, otherwise you return fail. That's the algorithm. We haven't really picked what is delta, what is t. These are all parameters that'll depend on the application. Cool, so that's the setup for matrix scaling. And this is the algorithm that we're gonna study from the perspective of convex optimization, right? So the plan is we can reframe this problem as minimizing a convex function. So the function that we'll optimize is this one. And it's just asking what is the size of the scaled input. This should remind you of the Kempf-Ness function or the capacity function that was defined in the last lecture, right? So we're moving through a scaling orbit and we're minimizing the norm. That should have some meaning, right? So we want to minimize over all e to the x, e to the y that are diagonal matrices with determinant 1. You can also see this as x, y that are diagonal matrices with trace 0. Again, these are just normalizations that don't that just affect how the problem is phrased, but like morally, we want to find the minimum norm element. And turns out that Sinkhorn algorithm is a descent method on this function. So Sinkhorn algorithm makes progress, like decreases this function towards the optimum. And the best part is that f is convex. So we are doing optimization on a convex function. And once we find the optimizer, those are exactly the double balanced scalings. And Sinkhorn step is a descent method, is a convex optimization method for this problem. Right? So that's the plan for the rest of the lecture, to show how to analyze Sinkhorn scaling for matrix scaling. Cool. So now, before we do the analysis, we just will mention some background definitions on convex optimization. Right. So what is a convex function? What's a univariate convex function is a function with second derivative non-negative. As a picture, like it always curves away from any tangent line. Cool. And H is convex everywhere if it's convex at every point. More generally, a function on a vector space is convex at a point in that vector space if for every direction, the univariate function is a convex function, right? And f is a convex function on a vector space if it's convex at every point in that vector space. And like the natural algorithms to study convex optimization are gradient descent. So we'll define the gradient, right? The gradient is a vector which tells you the direction of steepest descent, right? So it tells you if you take an inner product with any direction, that gives you the directional derivative of the function, right? So by some sort of Cauchy-Schwarz, the gradient direction is exactly the one that optimizes steepest ascent. Cool. Before we move on, I'll give one more definition of convexity, which will be helpful to study like why convex optimization is so much easier, right? So as I mentioned, the function curves away from any tangent line. So this is the formalism of that. So for any 2 points, the function at y is at least the function at z plus the linear approximation. So if you take a point z and then you look at the linear approximation to y, the function lives above that. Cool. And what that means is if you have something with gradient 0, if you have a point with gradient 0, then the function must live above this linear approximation, right? Which means that that point is a global minimum. There can't be a point lower than it. Mm-hmm. Cool. So this is why it's much easier to do convex optimization than regular optimization, is that if you just find a point with gradient 0, which is a local minimizer, then that's in fact a global minimizer. Cool. So now that's the setup for what is convex optimization, and it turns out that that's almost exactly what we're doing in Sinkhorn scaling, right? So our plan will be to study Sinkhorn scaling by showing that FA is a convex formulation for matrix scaling. And what does that mean? We'll have to show two things, right? First, that the doubly balanced scalings are exactly the critical points, which are the global minimum of this. And the second thing is that this function is convex, right? So then it's enough to go find the global minimum of this function, or even a local minima, and you'll find a doubly balanced scaling. Cool. So the first thing we'll show is that a scaling xy is doubly balanced if and only if the gradient at that point is 0. And how do we show that? I'll use this trick a bunch. It's a simple exercise to work it out, but there's a really nice invariance with respect to scalings of this function. So instead of looking at the function with respect to matrix A at point xy, you can instead look at the function at the origin with respect to point e to the x, a, e to the y, right? So that means that we can reduce lots of our calculations to the origin. They should be easier, especially in the non-commutative setting, they'll be much easier there. So all we need to verify now is, given a function which has the origin as a critical point, does that mean that that matrix is doubly balanced, right? And so that means that in every direction, the function does not change, right? And so this is because of the log, there's a ratio, and this is what it works out to. So what that means is you have every direction is taking an inner product with the row in that direction, and every column with the column. And since we are restricting to the case where these matrices have determinant 1, we know that this trace is 0 for both these xy vectors, meaning you can remove the traceless part from this formula, right? So in fact, you can write this according to the gradient as the inner product of x with this gradient, which is the difference between the row sums and the uniform vector, and the column sums and the uniform vector, right? So by this formulation, the gradient is 0 exactly when the matrix is doubly balanced, right? Exactly when these vectors is 0. So any critical point is a gradient 0, happens only when the matrix is doubly balanced. Cool. The second lemma we need is that f is convex, right? So we've shown that it's good to find critical points of this function, and if the function is convex, then in fact you can just search for local minima, and that's much easier usually, right? So again, by equivariance, by that same trick, you can move to the origin, and we just need to verify that at every point, or equivalently at the origin, the second derivative in any direction is non-negative, right? And once again, so you take a derivative, and you should get a sum of squares and another square. It's not particularly important what the formula is. It's just this is non-negative if you view the function as a variance of xi plus yj with respect to the distribution defined by these entries, right? So this is e of x squared minus e of x whole squared, right? So that's the variance of a function. That's always non-negative, right? So at any point in any direction, this second derivative is non-negative. Cool. So that means since by the trick to shift to the origin, this function is convex everywhere. So we've shown that the critical points are doubly balanced scalings and the function is convex everywhere, right? And then finally, how are we analyzing sinkhorn? Sinkhorn is a convex optimization algorithm, meaning it makes progress like for a convex function. So it moves closer to the minimum. And in particular, it moves faster if you're very far from doubly balanced, right? So what this says is if the matrix you're at has a large error from doubly balanced, that in fact sinkhorn scaling will make a large step in progress. How do we show this? What does sinkhorn scaling do? Remember that we have to maintain the determinant 1 property. So what sinkhorn scaling does is actually plays xi is the row sum, the ith row sum, and then normalize to make the determinant 1. Cool. And now we can just open up what the function does at step 1, right? So it plays x comma 0. This is equal to, we've normalized each of the rows, right? And you'll come out with the old matrix minus this exact distance from doubly balanced, right? So when this is large, recall that this is the distance from doubly balanced. When this is large, you're making a lot of progress. This last inequality was just a robust version of AMGM. It's a Taylor approximation with some calculations. It's given in the original paper on operator scaling. Cool. So that was the last step we've shown, right? So we've shown that critical points are doubly balanced scalings. The function is convex. And if you're far from doubly balanced scaling, then in fact, you'll make progress, right? So what's left to show is that sinkhorn scaling converges quickly and you get this 1/delta convergence, right? So what is the goal of matrix scaling is we want to output a delta doubly balanced scaling. And what happens is sinkhorn scaling produces a delta doubly balanced scaling in O of 1/delta iterations if you have some bound on the optimizer of the function. Cool. And the proof of this is quite simple. You just chain together the 3 things that we said, right? So every step, if you're far, you're making progress. So you have this bound on the function. You know that after t steps, you must be, by telescoping sum, every step you're, let t be the first time that you have delta doubly balanced matrix, right? That means that each time step before t, capital T, you must have more than delta error to doubly balanced. So at each time step before that, you're making more than delta progress, right? So for each of these t steps, you're making at least delta progress. And so if you just rearrange this inequality, you get that t is at most 1/delta, depending on the lower bound of the convex function that you have. Cool. So that was the setting for just standard convex optimization. It's not clear where you get this lower bound. In the application by LSW, they studied how to distinguish whether the permanent is 0 or how to approximate the permanent. And so in that case, they actually had a lower bound by some pre-processing step. In our case, we can actually assume something further. By our case, I mean, in the statistical application we'll have later, we can assume that our input is strongly convex, whatever that means. And that means we'll even get a much faster convergence of the algorithm. So back to convex optimization, recall that a function is convex if every second derivative is non-negative. A function is alpha strongly convex if, did it get cut off? Yeah. If the second derivative is at most alpha, or at least alpha, sorry. And turns out that, recall that a convex function, all the tangent line live below the function, right? This says that the function actually curves away from the tangent line quite strongly, right? So that means that if you have a point with small gradient, that's what h prime is, then you'll reach the optimum quite quickly, right? Because your function is curving upward quite fast, right? So what this says is for any alpha strongly convex function, you have a lower bound, a much stronger lower bound on the optimum in terms of the gradient at this point. And in fact, you have a bound on how far the optimizer can be away from t. Cool. We'll use both these ideas for like when we analyze more complex functions. But before we move on, we'll just raise this to vector functions. So a vector function is alpha strongly convex if every univariate restriction is alpha strongly convex, where the univariate restriction is with respect to, let's say, a unit vector, or more generally, if you take a univariate restriction with respect to v, then you must be alpha v squared strongly convex. And what's important here is that I get to pick a norm in which I'm strongly convex. So I'm curving away from the tangent line in some specific measure of distance. And since this is just a lifting of the univariate function to vectors, we get some of these properties again, right? So we have a very strong lower bound on the optimizer, and we'll have a distance bound on the optimizer. Cool. So this is a more abstract setting just about strongly convex functions. But in general, when your function is strongly convex, you'll get much faster convergence of algorithms, right? So in particular, if f is alpha strongly convex, then the gradient shrinks to delta in log 1 over delta steps, not in 1 over delta steps. And how do we show this? We just need the steps from before, which show a strong lower bound, right? So what we have is let T1 be the first time when your gradient size is halved, right? And we'll follow through by induction and say every 1 over alpha iterations, your gradient size halves, right? So let T1 be the first time that it's half. At this point, you have because the function is strongly convex, you have this really strong lower bound on the optimum, right? So there's only so much distance you can descend before you reach the optimum, right? And for each of these T1 steps, you're making significant progress by some descent algorithm, right? So for each of these T1 steps, you're making at least half of the original gradient size progress, right? So since we chose T1 to be the first time that you half, every time before that is at least half of the original gradient. And so if you rearrange this, you get T1 is at most some constant times 1 over alpha, right? So every 1 over alpha steps, you'll half the size of the gradient. And then if you continue this process, you'll get 2 to the minus k and k over alpha steps, right? So you get this log 1 over delta convergence for strongly convex optimization. Really, we can actually weaken some of these assumptions. We only need a strong convexity on the univariate restriction from any iterate to the optimizer. So that might be easier to get. We don't need strong convexity everywhere. And sinkhorn scaling that we're studying, like we're going to study sinkhorn scaling using the strong convex framework. It's a descent method. So actually, if you want to have strong convexity between every iterate of sinkhorn scaling and the optimum, it's enough to have strong convexity on a level set because sinkhorn scaling always decreases the function at least, right? So once you're within the strongly convex level set, you'll always stay in the strongly convex level set. This observation is due to Franks and Moitra in their application list 6. Cool. So these are the two things we want to study sinkhorn scaling, right? That there's some level set with which you're strongly convex the whole time. And how do we get this? There's a nice theorem by Chu Kwok, Lapchi Lau, and myself that worked on these kind of sufficient conditions for when you have strong convexity around the optimizer for a large ball, right? So what they say is if you have a matrix and it's epsilon doubly balanced and it's alpha strongly convex and alpha is much larger than epsilon, then in fact, your optimizer is nearby. And further, the whole ball around the optimizer is strongly convex. So very quickly, sinkhorn scaling will reach this strongly convex ball, and then I'll stay inside the strongly convex ball. Cool. So this is it's a little bit harder to ask for strong convexity of the optimizer if you don't know anything about the optimizer. So this allows us to reduce from just strong convexity at the original point. Cool. And so what this tells us is by the same strongly convex optimization analysis that we just did, that with the same conditions as above, if you are epsilon doubly balanced and alpha strongly convex as a matrix, meaning epsilon doubly balanced and the function fa is alpha strongly convex at the origin, then you get the same log 1 over delta convergence of sinkhorn scaling, right? By this exactly the same analysis as above. Cool. So in conclusion, we've covered how to frame matrix scaling as convex optimization, and how strongly convex inputs will give a improved analysis of, let's say, the optimizer or of algorithms. These are the kind of ideas that we're going to generalize to the geodesic setting for non-commutative optimization, which we'll talk about in the next lecture.
Great.